This video explores work on spatial thinking. The article from Mind, Brain and Education searches for associations between subcomponents of mental imagery and mathematical calculation. Definitions of spatial visualization sometimes include a reference to visual representations as well as spatial transformations. The researchers, therefore, try to delineate the role of spatial transformations and visual representations in mathematical calculation. Numerical competencies relate to an understanding of number symbols, their relations, and applications. Cognitive training studies have demonstrated transfer of gains from spatial visualization training to numerical competencies, including calculation performance, symbolic number comparison, word problems, and place value. This could be if spatial visualization happens to provide a mental chalkboard on which numerical relations and operations can be modelled and visualized. Mental imagery, MI, is the ability to create and manipulate images in the mind in the absence of sensory input. It appears that while we can all see with spatial and visual accuracy in the mind's eye, the visual quality of MI differs across individuals. Koslin's separable component model proposes that MI is comprised of distinct components, namely image generation, image maintenance, image transformation, and image scanning. The authors hypothesized that all subcomponents of MI will be associated with mathematical calculation. They did not have a predefined expectation as to which subcomponent will explain the most variation in mathematics performance. Both age and mental rotation were significant variables in the final model, with mental rotation accounting for 5.9% unique variance in calculation skill. There were no significant associations between other subcomponents of MI and calculation performance. Findings of differential associations are supported by evidence of neural activation differences that also show dissociations between spatially transforming information and visually representing information. The authors identified that spatial transformation may have a closer neural link to number skills. Transfer effects from mental rotation training to improvements in mathematics calculation can be interpreted in the context of spatial transformation strategies and visualizing strategies. The authors prefer the spatial transformation strategy to explain the transfer. The spatial transformation strategy suggests that children complete calculation problems by mentally manipulating and restructuring equations. MI, and more specifically mental rotation, are important to calculation skills. Spatial transformation, and to a lesser extent visualization strategies, are valuable to calculations. Each of the skills or strategies above should be incorporated into mathematics teaching at all times. If MI strategies and skills are introduced before corresponding content, students will have strategies in place to transfer across to the numerical content. Much credit to all of the sources and authors from which I reported on their work. For further information, please feel free to leave a note in the comments. If you found this video helpful or informative, please click the like button. If you want to see more videos on education and neuroscience, please subscribe. Thank you for watching.